Hey guys, so in the last video, we talked about the uncertainty principle. We actually derived the Heisenberg uncertainty principle. We derived the general uncertainty principle and then showed how it related to the Heisenberg uncertainty principle. And what I want to do in this video is take a step back from all the math and the hard math physics that we've been doing and go back and think about what does this all mean. And this is actually a very big question in quantum mechanics. So this is an important video. It's not going to have much math. But I want to start by summarizing our result into words, more of a conceptual understanding of the uncertainty principle, which is if the commutator of a hat and b hat is not equal to 0. Is not equal to 0. Right? So if a hat and b hat, the commutator is not equal to 0, if they do not commute, then a and b cannot be known at the same time. Right? And this is actually a pretty significant statement, right? We have quantities that we cannot know at the same time, right? And so let's think about this back to our hardness and our color and hardness video, right? We could have, right, our two observables is being is color and hardness, right? It can, and the quantities, right? So those would be like the operators. The eigenvalues would either be some value corresponding to white, some corresponding to black, or for hardness it would be hard and soft, right? And actually later, I think that in like chapter 7, we'll actually figure out what those eigenvalues are, what the actual numbers that represent hard and soft and black and white are, and what their operators are, right? But if you had some color operator and the hardness operator, their commutator would not be equal to 0. Right? Their commutator would not be equal to 0 because you can't know them at the same time. Right? We showed in the Stern-Gerlach experiment we can't know color and hardness at the same time. Right? And so one other note, just what we're going to try to do in quantum mechanics is we're going to try to find what is called the CSCO. CSCO. This is what we're going to want to find in our problems. This is the complete set of commuting observables. So, complete set of commuting observables. Right? And what this means, right? Two commuting observables, right, are observables that you can know at the same time, right? So this is all the observables that we can know a value for at the same time. Right? And so that's going to be one of our big problems in quantum mechanics, trying to find the complete set of commuting observables so that we can, know everything that we're allowed to know about the system at once. But there's there's a little bit of a problem here, which is this really goes against our physical intuition. Our physical intuition tells us that, just like if we have, a ball rolling down the hill, we can know the ball's mass and its speed and its position at the same time, right? There's no inherent uncertainty. And that, that makes quantum mechanics seem a little bit difficult because we just showed that there are things that we just can't know at the same time, like position and momentum, right? And so this has prompted a lot of discussions and a lot of debates between physicists who have this quantum theory, and they try to figure out, how can we make any physical sense of this? Quantum mechanics works. The experiments say it works. But now we have to deal with the fact that we live in a world where there's inherent uncertainty about certain things. And in this video, I want to talk about the interpretations of quantum mechanics. And the interpretations tell us what to make out of this inherent uncertainty and other weird things that quantum mechanics does. So the first thing I want to talk about is the Copenhagen interpretation, right? Which is going to be our big one. And I'm going to talk about the Copenhagen interpretation, especially because most physicists subscribe to this. Not all, but it is generally considered the standard interpretation of quantum mechanics. And the Copenhagen interpretation gives maybe even a very unsatisfying answer. But it's that, right, if we're talking about, the question is, why can't we know position and momentum at the same time, right? It's that the particle does not have a position and a momentum in the way that we think of it, right? It's not that we just can't know its position or we can't just know its momentum. It doesn't have a definite position and it doesn't have a definite momentum until you measure either the position or the momentum. It is in, it's in a superposition, right? This goes back to our idea of superposition, that there's an inherent superposition in nature. That asking, what is the exact position of this particle when you haven't measured it makes no sense. It's in a superposition of different positions. It's in a superposition of different momenta. You can't say what it is, right? And, in one of the other consequences of this interpretation is that if you're measuring, right, if you measure the position or say you measure the color, right, just like this, before you measure the color or the hardness, we'll get back to this in a minute with Schrodinger's cat, it doesn't have a definite color or hardness. It's in a superposition of being black and white and being hard and soft. It doesn't have a definite value of either of those until you measure it. Right, and one of the consequences of this is one of the consequences of having this kind of interpretation is on experimental accuracy. That you might think, well, we just haven't come up with a device that can measure the hardness without messing with the color, or a device that can mess with the color and not mess up, or that can measure the color and not mess with the hardness. And what the Copenhagen interpretation says is that any experimental device that you come up with, any way to measure color, the perfect method still will mess with the hardness. It is absolutely impossible, right? And people often explain the uncertainty principle by, you've got a particle here, right? And then you measure it, but when you measure it, you find its position, but then, you send a photon at it, which imparts momentum, and now it's got a weird momentum. Right? Which is sort of right. The Copenhagen interpretation is saying that any experiment that measures position will also impact momentum. But the other thing is, it also says that particle doesn't have a definite position until you measure it. So that's those two parts, that there are no quote-unquote perfect experiments where you can measure position without affecting momentum, or you can measure color without messing with hardness. The Copenhagen interpretation says that's impossible. No matter how much technology, it is entirely impossible to come up with that kind of experiment. It violates the laws of physics, right? Now, the thing with it, not having a color, not having a hardness is very difficult to understand. And so there's a thought experiment called Schrodinger's cat that you may have heard of. And I'm going to erase this. Hopefully you have it down, or you understand it. Right? And we're going to go back to Schrodinger's cat. And in this thought experiment, I have a box, and I have a cat inside the box. Now, you're going to have to excuse me. I am a horrible artist. It looks like a horrible cat, but it's okay. And I've got a radioactive substance in here. Okay? And the box is closed, right? I cannot see what's on the inside. Now, for the ease of seeing the drawing, I'm not gonna, right? I'll leave it like that to just show that the box is closed. And you can't see within this box. Now, this radioactive substance has a 50% chance of breaking. Oh, if give it a certain amount of time, wait an hour. In an hour, it has a 50% chance of of the radioactive substance breaking, which would kill the cat. Right? And I know this is very cruel to animals, and you know, it's probably not a great thing to do, you know, in real life, but as a thought experiment, it's a bit cruel, but it's okay. Not that cruelty is okay. So you have this cat in the box. It could die when this vial of radioactive material breaks, or it may not break. You don't know. Now, the other thing we have to do is we have to think that there is a caveat to this, that people will say, you know, oh, but you could just do that. You could just look inside the box, right? I mean, or actually, you'll see in a second. I'll show you where people have a caveat, and this is where you have to imagine this cat obeys the laws of quantum mechanics. It's not a perfect analogy. There are no perfect classical analogies for the weirdness of quantum mechanics, but we'll try here. Right? You look in the box, and the question, before you look in the box is closed. The question is the cat dead or alive? So, is cat dead or alive? Right? And this is a question, right? And the answer is it's in a superposition. So, in a superposition. Right? And you could write this as the state of the cat. State of the cat is equal to 1 over root 2 being alive plus 1 over root 2 of being dead, right? And if you square these, you'll get that it's 50% chance of being alive, 50% chance of being dead. Right? And now you might say, well, the cat is either dead or alive, you just don't know until you open the box. And this is where you have to buy that this is a quantum cat, because the cat, until you measure it, is truly, so it's not alive, and it's not dead. It's not both. It can't be both, right? You can't be both dead and alive. It's one or the other. It's not either of them. It's not alive. It's not dead. It's not both, and it can't be neither. Right? It's in a superposition. And that's some of the weirdness of a superposition, that it's not one, it's not the other, it's not both, it's not neither. It's not either, it's not neither, it's not both. It's in a superposition, which is a very weird concept, but it's something in quantum mechanics that we have to deal with. And the Copenhagen interpretation is going to say that this cat is not actually alive or dead. And again, the quantum cat, where it obeys quantum mechanics. This cat is not alive or dead until we open the box. It is in a superposition of being alive and dead. Once we open the box, we'll know. And this will no longer be the cat state. We'll measure it. Right? And so that's the Copenhagen interpretation. That the cat is not alive or dead until you measure it. Right? It's in this inherent superposition state. Now, this worried a lot of people, and we'll look at later the EPR paradox, which is basically Einstein's response to this, because him, like I'm guessing many of you, think, you know, he thought, this is just too weird, right? This is not possible. You can't like, you know, have certain things that you can't know at the same time. That's not reality. And he wrote this famous paper with 2 of his students, I believe, Podolsky and Rosen. We'll talk, I think I'll have a video about that in a while in Section 8, where we go back into that and sort of look at what quantum mechanics says about them and how this problem ended up getting resolved. He advocated for what's called a hidden variable theory. And the kind of hidden variable theory he really wanted, which is called a local hidden variable theory, is what you might initially think, which is the cat is either dead or alive. We just have to measure it. right? And once we measure it, we'll find out. But the information's there, we just have to measure it. And this is very tempting to go with. Classically, it makes sense. But actually, there was an experiment in quantum mechanics that ended up disproving, saying that there is no possible local hidden variable theory. It basically discredits that theory, which is a very weird thing to do. And so the details of that we're not going to get into right now, but probably in section 8, I'll get into that. It's Bell's theorem and Bell's experiment. So it is very, very weird that this cat is not dead or alive until you measure it, right? And it doesn't have this state until you measure it. It's very weird, but that is the Copenhagen interpretation of quantum mechanics. Now, I will give one other interpretation, partially because I think it's just really, really cool, and also because it's I don't know if I'd say highly used. I would say probably a lot of scientists do not subscribe to this theory, but it is a theory. It's an interpretation, and it's called the many worlds interpretation. Right? And what it says, similarly to the Copenhagen interpretation, that the cat is not dead or alive, right? It's in some superposition until you measure it. But when you measure it, it's not like it's forced to choose. In the Copenhagen interpretation, that's what it is. But in the many worlds interpretation, there are actually two separate universes, right? Or multiverses. There are two separate universes. One where the cat is alive. One where the cat is dead. Right? There are two separate multiverses, and you don't know which one you're in. You don't know which universe you're in until you measure it. And once you measure it, you pick one of these two paths. You're either in the universe where the cat's alive or the universe where the cat is dead. Right? So measurement actually picks which universe you're in, which is a very weird, interesting, and pretty cool concept. And this is actually something that a lot of scientists do believe. I don't know if a lot might be a debatable term to use there, but it's a legitimate theory as to the interpretation of quantum mechanics, and it counts for it, right? Just like the electron, when you have the electron, there's a universe in which the electron is white and a universe where the electron is black. And you don't know which universe you're in until you measure it, and then you figure out which of these alternate universes you're in. I don't know. I find the many worlds interpretation, right? There are many different worlds. That's where the name comes from. I find it very interesting. I believe it was a scientist named Everett, a physicist named Everett, last name, that I believe came up with this. It's pretty interesting. Now, Copenhagen is, again, the far more standard, although it is very unsatisfying to think about. That the answer is just that, you ask, is the cat dead or alive? The answer is, it's in a superposition, 50% chance dead, 50% alive. Until you measure it, it's not dead or alive. Very weird, but that's the Copenhagen interpretation. That's more standard, but then you have this many worlds interpretation. Okay, so with that, I will see you in section 3.